which way would his hand go relative to the stick? Therefore, which way is friction acting on his hand? So I have friction acting down this way. And up this way. And I didn't give myself really enough space for a proper room here. And some of you might see me do this on your test if I just need to somehow separate them so that it's easier to keep track. Anyway, test number problem. It presumably will be the next to the last problem on the test. Test 1B. Stephanie.
There not be normal force on the rope touching something?
All right, how is the rope attached to, we'll just say, the box?
Oh, we don't know.
We don't know, that's why we're lumping in attention.
Okay. So if it like specifies that it's like tied around the box or something.
Yeah, then it would, then suddenly, if it's tied around the box, then we're talking about a normal force there. I haven't done that level yet for it. Yeah, then you're sort of in that rope pulley situation where there's a normal force. They gave you that level of detail.
Would that make the rope not ideal?
No, you can still have.
So the rope would still be ideal, even if it were tied around the box.
Yeah, we assume that it's, there's a magical property to it that even though it's frictionless, it can still tie into a knot and not unravel. It's
Okay.
elven rope. Looking for recognition, it seems like there's one person who recognized the reference. Okay, moving on.
I'm feeling like it's Lord of the Rings reference.
Oh, yeah.
I never watched all of Lord of the Rings. I watched most of it. But then Mom got scared of Gollum and I was forced to stop.
Okay,
Don't ask me. Don't.
well, you probably can handle it better now.
Oh, I could. She couldn't. She's also 34 years old.
Questions?
Are we gonna do another practice?
One, we're actually going through the full analysis.
Okay.
You
Are we
will
gonna
have a
do
chance to practice another one of these on, say, master sets, applications, concept or 5, as well as, I got old test posters.
Are we gonna do another one anyway since we have 20 minutes left?
We're going to work through a problem. Why don't we work through the double round?
You said with the old text, do you have the answers on there?
For some of them.
Okay.
Some of them, there should be solutions written out. Some of them, like, just have the test with no answers.
And will they, for the ones that do have it, are they like that level of detail written out?
If I have answers for the force diagram problem, yeah, it should be written out
Okay.
like that. There was one where I've got a bunch of handwritten, and then I took a picture of it, and that's because I had a student come in and said, I would like a solution for this test, these problems. And so I did that.
Have you made any rule against that since then?
Have I made any what?
Rule against that since then?
No.
Cool, so we could do the same thing?
Yeah.
Cool.
All right, I know I just erased the force diagram that we're about to use, but we can simplify this a little bit. So let's go ahead and start out with we're dealing with a frictionless surface.
Is that a micro or an M?
That is a mu. As a prefix, it stands for micro. Here it stands for the coefficient of friction. Coefficient of static friction, coefficient of kinetic friction.
Oh.
This is just shorthand for saying it's frictionless. We'll make that 5 kilograms, make that 3 kilograms. Make this a 30-degree angle, and make that angle theta sub 3. So the first part of this is assume that we have two masses on a frictionless double wedge. They are in equilibrium.
So,
What is the second angle?
30.
the second
If the-
angle is in the one with the pulley?
No, the angle, the one that's labeled theta sub 3.
Oh.
And
What?
it's not guaranteed that this angle is 45?
It's not
90.
guaranteed anything what that top angle is.
Okay.
All right, so we go through the steps. We've already done the force diagram, so I'm going to sort of jump to the chase there, except I'll do different subscripts. We have weight of 5 acting down. We have tension acting this way. We have normal force of 5 acting that way. And then for the 3 kilogram mass, I've got the weight acting down, normal force, and tension. There should be the 3 forces we had acting on it before, minus the friction. What is the direction of acceleration?
Is that an S or a 5 on
It will probably be a 5.
the, okay.
Oh, well, unless you're talking the use of S at the top, but that's about it.
No, I'm talking about the blocks with the
Yeah. That'd
isometric.
be a 5.
Okay.
Will
Direction.
acceleration be like either up or down?
I gave information and wording of the question that you would know. We state it again.
So they're,
I have the 2 boxes. Oh,
so they're in equilibrium.
Yes.
So there should be no acceleration.
Yes.
that's the key.
That's true.
The other clue, if I said it moves at a constant velocity, that's another clue that it's in equilibrium, acceleration is 0. Now, is it moving or not? Doesn't matter, does not change our answer. All right, so acceleration is 0, so we don't have a preferred direction of acceleration. No, sorry, ignore that, 0. So when we come to the coordinate axes, we typically want in the direction of acceleration, but since there is no direction of acceleration, or unlimited directions of acceleration, we have a lot more freedom to set up our coordinate system. I would recommend you be somewhat consistent. Just sort of imagine that it's going to slide one way or the other. So I can either imagine it's sort of swinging leftwards or rightwards. It doesn't matter, pick one.
Rightwards.
So I'm going to set up my system so that I'm going to call this I3 hat and J3 hat. And over here, oh, that's not consistent. So if that's going this way, then this one's going to be going up. So this is I5 hat and J5 hat. Decomposition. Have we done decomposition for box on ramp?
Box on ramp, just a normal ramp?
Yeah.
Yeah, I think so.
Okay. All right, first off, given our coordinate system, the fact that it's down the ramp and away from the ramp, are any of these forces not in the direction of I3 hat or J3 hat? Plus or minus?
Why? Normal force.
Normal force is in the J3 hat direction.
Oh, my bad.
Would weight?
Yeah, weight is not. The tension is in the negative I3 hat. Y sub 3 is in the J3 hat. Weight is in a combination of I hat and J hat, so we need to break that up. So decomposition is gonna happen to this. So I need to break that up. What about over here with its coordinate system? I5 hat and J5 hat. Which of these needs to be broken up?
Wait.
So those are what we need to decompose.
And is that D?
Yes, that is the D.
Okay.
So looking at just the right-hand side, I have weight that is acting down, and I'm breaking it up into a vector that is parallel or anti-parallel to each of my coordinates. In other words, I have weight acting down like this, and I am breaking it up into a component down the ramp and into the ramp. Whatever I'm breaking up is the hypotenuse of my right triangle. And I know that either this angle is going to be theta sub 3 or that angle is going to be theta sub 3. One of them is. Well, let's do a little geometry. So if that is the weight I'm breaking up, this is my angle theta sub 3. So I have two right triangles here. I've got the larger right triangle, which is sort of representative of the wedge itself, and then the smaller triangle here, which I weight as the hypotenuse. If this angle here is theta, and that's a right angle, what is this angle here?
Theta?
Yeah, it's the complement. Now I shorten that to just theta prime. That's the symbol that I use for the complement of theta. I know that this is a right angle here. So if this angle is theta prime, then what is this angle?
Theta.
So this angle down here is theta, so the part that is acting down the ramp is opposite to that. So this is going to be the hypotenuse times the sine of that angle, and this will be the hypotenuse times the cosine of the angle. So I would break up that weight into, basically have a new force diagram for that. These stay the same. Acting down into the ramp is going to be weight sub 3 times the cosine of theta sub 3. And down the ramp would be weight sub 3 sine of theta sub 3. Now we have to break up weights of 5. Now what the part that's going down the ramp, given that the angle I gave you was against the horizontal, it's going to be sine of 30 degrees down the ramp, cosine of 30 degrees into the ramp. I'll first write that down, then I'll talk about an alternate way of finding it. So I've got tangent acting up ramp, y sub 5 acting away from the ramp, w sub 5 cosine of 30 degrees into the ramp, W sub 5 sine of 30 degrees down the ramp. Now let's suppose you're getting in, you have a quiz or a test or a master set or something like that and your mind's blanking. If you don't solve it in time, the bomb's going to explode, lives will be lost. You know, typical physics problem. And you're trying to think, all right, which one's sine? Well, I know one's sine, one's cosine, which one is it? Well, another approach that you could take is try to draw it more realistically than I did. A 30-degree angle does not split the quadrant. A 30-degree angle is closer to the horizontal than it is to the vertical. That's closer to 30 degrees than what I drew over there. I'm going to break weight up. So weight is acting straight down. I'm going to break it up into components. That is a right angle there. I know one of these will be the weight times the cosine, one will be weight times the sine. Well, if I plug into my calculator sine of 30 degrees and then cosine of 30 degrees, I'm going to get a larger number for one of them. The larger one will go for the larger vector. Cosine of 30 degrees is bigger than the sine of 30 degrees, so this will be W cosine 30 degrees, and this will be W sine of 30 degrees. And get to the same place we did there. Questions here?
Would the opposite side have the sine?
Well, this angle here is 30 degrees.
Oh, okay.
All right, that's decomposition. Now the equations of motion. If I've done this properly, equations of motion should be relatively simple. I know F equals ma. How many equations of motion will I have? Why two?
There's 2 boxes.
But each box will have 2. It's the number of dimensions per item. So I have 2 boxes, you're right. This box has 2 dimensions, this box has 2 dimensions, and so I'll have 4 total. There'll be an I3 hat equation, a J3 hat equation, an I5 hat equation, and a J5 hat equation. So those are going to be my 4 equations. And F equals ma is my template. Equations of motion. I'm sure I said it last week, but I'll say it again. Equations of motion are not the equations from chapters 2 and 3. Equations of motion are plugged into F equals ma. All right, so we look at let's say the I3 hat equation. What are all the forces in the positive I hat 3 direction?
Weight times sine 3. Yeah.
Right.
Yeah.
So I have weight 3, sine beta 3. Minus all the ones in the negative direction. Negative I3. Hat.
The tension.
Yeah, okay. Equals mass times acceleration. Mass of 3 times the acceleration.
And acceleration is not a vector in this case?
All of these are in the I3 hat direction, so
They are.
these are all the magnitudes of vectors that are running in that direction.
So they're scalars until they have direction.
These are, at this point, they are scalars.
Okay.
Can we not put the kilograms in for mass?
We could. I was going to save the plugging numbers in until the end.
Okay.
Now, as far as when to plug numbers in, you can plug numbers in whenever you want. It's generally recommended when teaching it to plug numbers in at the end. And there are actually cases in which it is convenient to do that. But if you plug numbers in at the very beginning, that is not wrong. You might cause yourself a little extra work later, or depending upon the problem, it might be easier. If you get far enough in physics, eventually you stop dealing with numbers.
Good to know.
And then you start working on your master's or your doctorate, and numbers pop back in. All right, J3.
Normal minus the cosine.
I will go with the spirit of what you said.
Yeah, sorry.
Equals.
That's what makes it mass times acceleration.
Say it again.
Mass times acceleration. So,
That's 3 kg. Times acceleration.
Well, the mass will ultimately be in kilograms, but what is the acceleration? Zero. The whole point of picking coordinate system, well, actually, this acceleration will be zero also because it's in equilibrium. So that equals zero. But this one is going to be equal to zero even if it were accelerating because the acceleration is going to be parallel to the ramp and J3 hat is perpendicular to the ramp.
So when you picked J hat and I hat's direction, can you just assign one of them to a direction?
Wait, if you've done what?
Like when you were picking what direction I hat and J hat would go in, could you like swap I hat and J hat?
Yeah.
Okay.
And some people do. I'll tell you, I get my mind set on I hat, J hat being in particular directions, and then I see somebody get answers backwards, and I'm thinking, wait, what? And then I look to see that they defined it opposite the way I would. All right, now, the I5 hat.
It's friction. I'm sorry, wait. The tension. I apologize. Minus the weight sub 5 sine 30 degrees.